A very good evening. Welcome to the week 9 doubt clearing session on fundamentals of additive manufacturing. Uh, I'll be starting with a brief introduction to all the topics that has been covered in this week 9 lectures. So I would like to ask you, whoever has joined, so have you gone through the videos yet? Hello, can you hear me? No issue. I would like to start today's class with the recapitulation of the topic, the first topic that has been covered in week 9 lectures, that is powder aim. So in last class, if you remember, we have gone through the process called YM, which is wire arc additive manufacturing. WAM is a process where a wire of metal is used. Only metal as a raw material can be used, and it should be present in a wire form. Now the wire was getting melted using the arc source or the plasma source. The plasma aim was also there. These all type of processes come under the umbrella of directed energy deposition. WAM is one of the DED process. Now today we are going to use the powder-based DED process, where in directed energy deposition, the powder is fed from a nozzle. There is another type of powder aim as well, in which powder bed fusion will take place, like the powder will be present on top of the substrate and it will be spread on top of the substrate instead of feeding. Here, powder feed based aim will be discussed, where the powder will come through the nozzle along with the laser. So, as I said,
Excuse me.
laser, yes,
Yeah, today it
yes,
is supposed to be week 9, no? Like
week 9, yes, this is week 9
electron
only.
beam. I think
This,
it is begin with the electron beam building.
I was having these three notes.
Okay.
Electron beam gun, these
Yeah,
you are
those.
talking about? Okay, this was the
Yeah,
beginning you are saying.
yeah. In the beginning, that is there.
Okay. Then, okay, we can start with the electron beam based wire additive manufacturing. So,
Yeah,
electron beam is basically the beam of electron which is coming from an electron gun, and it's similar like an arc or like a laser source. It's basically an energy source which is able to or which is capable of melting the metal. This
yeah.
is the electrons emission and the normal process or spontaneous emission of electrons. If you put the heat from the conduction band, the electrons come out. So if you put the photons, the electrons come out, secondary electrons come out. So by which you can get the electrons out of the gun. That is a normal reaction. If you put the energy in the electron gun will emit some electron, and if you somehow can focus the emitted electrons to a particular spot, then you can call it as an electron beam, which can be useful for the melting of the metal. As it's an
Fine.
electron beam, it's yes. So as it's an electron beam, not a light source, for example, like laser. So the normal lens doesn't work here. The important thing is here we use the magnetic lens. Basically, instead of normal glass lenses, we use magnetic coils where the electromagnetic field will be created in such a way that from both the side, the electrons will get the repulsion and they will try to get accumulated at one spot, that is this red beam, and thus you can focus the beam on top of the substrate. Now, electrons are very, very light element. They are very light in weight. So that's why the weight, the presence of air in the chamber will not be very helpful for the electron beam to come. The electron may get repelled from the air particle, air molecules, and impurities present in the air, and they will not be focused on top of the bin plate. That's why we try to achieve as much vacuum as possible inside the chamber, like this, -7 to -9 bar at the thermionic gun, and like that we can achieve the proper focusing of the electron beam. So now I am having the electron beam. You can see here the electron beam is getting focused because of this uh, electromagnetic coils, which are basically getting the repulsion of the electrons
Excuse
so that
me,
they,
we are not getting
yes,
the. I'm not getting the slide here. The screen.
light screen is
I'm
not
not
showing.
getting
This
only
you can't
earlier
see.
slide. Only it is there. Yeah, earlier only that the classification of powders,
Oh, okay,
introduction
okay.
to
Let
powder.
me
Only
stop
that.
sharing and then share it again. Now, now is it visible?
No, only dark screen only we are able to see. I'm
Maybe
able
a
to see.
little network issue. I'll stop sharing and then I'll share it again. Let me know when it comes.
Okay.
I've already shared my slide and I'm in the 7th page of the EB-based SWAM process.
No, we are not. I'm not getting anything. Any slide.
Okay. Is it happening for both of you? Guru Murthy, can you see my
Yeah, for my
slide?
for for myself, it is not. I'm not getting. Only dark screen. I'm able to see.
Okay. I'm trying to figure out if it's my network issue or your network issue. Because the same network I use every day. It's still not there. Oh. I've stopped sharing and I'm sharing it again. Can you see it now? No, not yet. Am I audible? Hello. Can you hear me?
Yeah, but some interruption is coming
Okay,
in between.
this should not be done. And the slides are still not visible.
It's not, it's not clear. Screen is not visible. Even in audio also some interruption is there.
Surprising because this is a network I use every day. Maybe
Some disturbance is coming.
disturbance. So now the network is showing me full connection. So can you hear me now properly?
Audio also some break. It is breaking actually in between.
Still it's breaking. Let me rejoin the meeting then. Okay. Just wait for 2 minutes. I'll rejoin the meeting.
Okay.
Can you hear me now properly?
Mm, okay, to some extent okay.
And the slides are still not visible?
No, absolutely no.
Ah, I don't know what to do. Maybe you can open the slide in your computer and then just look into the slide. And I hope till when we are done with the slide, the network will be stable.
Now is okay. Now we are getting. Now I
Okay,
got that.
coming.
Screen now, yeah,
Okay,
it is okay.
this is moving. The slides are
Yeah,
moving. Yeah. Okay. Thank God. Okay. So
lights are not
yeah. So now we
air based AM.
yeah, yeah. This EV based wire based AM. Eighth slide. So now we know that using the magnetic coil, we can focus the electron beam. Now it's important to understand why we are using, first of all, the uh, vacuum chamber and how we are achieving the vacuum inside the chamber. Two things. So we are in the ninth slide right now, if you can't see. So first of all, the vacuum is important because, as I said, electrons are very lightweight particles and they're coming at a high speed. So if there is air particles, these particles may interact with the electron from the source itself and they can get deviated from their original path. The vacuum needs to be there. So to achieve the vacuum, there are various type of pumps which are available in the market. First one is rotary pump, root pump, diffusion pump, and turbomolecular pump. So these are few pumps that are used to achieve the vacuum or different level of vacuums. But we need the highest level of vacuum with the highest efficiency. So that's why we are using the turbomolecular pump here to achieve the vacuum inside the chamber. In the gun area, the vacuum is much more than the deposition area. So in EV-based wire aim process, the EB comes through the coaxial nozzle from from the perpendicular direction, and the wire is the side feeding one. So here in this image, the side feeding wire is shown here. So in case of side feeding, we know that there are multiple configurations which are possible, and each configuration give us different results. So based on what your aim is you can choose which type of feeding, side, front, back feeding, which is necessary. So the material transfer, the molten material transfer can be happening in two way. One is the droplet. So basically your wire is a little bit far away than your substrate. So this is your substrate. That means this is the melt pool that will be forming. And your wire is a little bit far away than this. So when the wire is interfering with the electron beam, there will be a molten material or the wire tip will be melted, and this melted wire will produce the droplet of the melted wire and it will come on the substrate. So it's the droplet transfer. Another one can be this wire is so close to it that out of the surface tension, when this droplet is coming, this will form a bridge with the previously deposited droplet on top of the substrate. So as a result of which, out of the surface tension, this molten metal will be transferred and deposited. Then EB based AM processes has a very prominent drawback, which is that as we are doing it in the vacuum chamber, the size of the part to be made has a restriction. So the size will be obviously not, the size cannot be very big in case of EV based processes. As we are doing it in a vacuum chamber, it's already a very costly process because we need to install the turbomolecular pump, and then if you are printing a very big volume, then you need to put a very big chamber with a very high energy pump, which will enhance the cost. So that's why, and also it's very difficult to create vacuum in a very bigger chamber. So size is one thing which is restricting, or as a drawback we can take it. Another is the surface finish, because here it's a wire based method, so the layers will be prominent. So you have to go for the post processing after the part. Now in case of VAM process, we have learned about the hybrid additive manufacturing process, where just after the deposition you can go for the milling operation and you can get rid of this undulated surface itself inside the machine. But in case of EV based method, it's not possible, because in EV based method your your chamber has to be small and you cannot incorporate that milling head inside the machine. It will again add the additional cost, which is not needed, because for milling vacuum is not needed. So this will be only AM machine with a little bit surface finishing problem and the restriction in the volume of the printing. This distortion and everything is shown here because it's a very high energy process. You are putting very high energy electron beam in each layer to print the whole job. So due to this repetitive heating and cooling, and it's also vacuum, so cooling rate is faster. So in that case, your residual stress will be a lot in your part and build plate, due to which distortion can be there. So then comes the process where you are using coaxial wire feeding. So the wire will be coming at the middle, and from three sources the electron beam is coming, or the electron beam is coming from one sources, but then you have split it into three beams, and now you're focusing these three beams from three side 120-degree apart using three different pair of magnetic coils, and you can focus the beam at one spot and you can deposit using this coaxial wire feeding. This will ensure the omnidirectionality, because here the wire feeding is not from front or back or side. So whatever geometry you're printing, whether you're printing a geometry which is twisted like this, or which is like a normal box, or which is like a sphere, your omnidirectionality in terms of printing will be maintained, so which is a big advantage in partial fitting. These are some EV-based systems given here. Although in India, I think there is only one or two EV-based systems are present because it's very difficult to maintain this electron beam-based any additive manufacturing process, whether it's powder bed fusion using electron beam or wire electron beam or powder fed electron beam because of the vacuum theme. Next is uh, so we have two PDF in so this is also lateral wire feeding omnidirectional. I think we will go through this PPT next. This is the second one. So now we are going to talk about the wire AM process using laser and electron beam. So now we are coming to the laser wire additive manufacturing. So just to point out a very important point, whether it's an electron beam based wire fed AM or it's a arc uh, wire arc additive manufacturing or it's a laser wire AM process, this all are coming under the state of the art called directed energy deposition. These all processes are known as directed energy deposition if I am coming from the classification of AM, because here the energy source and the feedstock or the raw material is interacting on top of the build plate, whereas both the things are coming simultaneously. It's not like one is stationary and one is coming. In all the process, the arc or wire or the plasma and the wire, the electron beam and the wire, the laser beam and the wire, all these pairs are coming simultaneously through the nozzle or through the tool, and they're interacting on top of the build plate first, then they are getting deposited. So that's why they all are under the directed energy deposition umbrella. So in laser based aim, now for laser, you don't need to have a very high vacuum chamber. It's okay to process in an open atmosphere, or it's better to process it in a controlled atmosphere with the or in the presence of an inert gas. As laser based aim process will deal with a very high temperature, high building rate. So it's important to maintain a controlled atmosphere to avoid any contamination or any kind of disturbance in the melt. So like that, we use argon gas normally. Argon, nitrogen, helium. These are few inert gases which will not interfere with your process, but it will create a hemisphere of the gas which will not let the air or the foreign particle to enter in your deposition zone. It will try to maintain the shape of the melt pool. It will try to reduce the oxidation of the melted bead, because while melting your instantaneous temperature will be very high, so there will be chances of quick oxidation. So to avoid this oxidation thing, it's important that you print the metal in the presence of any inert gas. Now, talking about inert gas, as I said, we have options like helium, nitrogen, argon. Helium is very lightweight, so it's not that recommended to use helium as an inert gas. Instead, we use nitrogen or argon because these are the two heavier gases, because we need to have a shielding using these gases. So your gas need, so need not to be very lightweighted that it may fly off very easily. So argon and nitrogen are used. Now it depends, or the type of gas depends on the material that you're printing. So it's very important to know that you do not choose this gas randomly. When you are using any material like aluminium or copper or stainless steel, we go for argon gases. But when you use maragin steel or some type of steel, we use nitrogen gases because in some steel, when you deposit the steel in the presence of nitrogen gases, your hard phases may get entrapped in your deposited bead. So there can be the phase evolution because of the shielding gas itself. So that's why the road. Yes, sorry. You have any doubt? So the role of shielding gas is very important. So next is that the manipulator is very easy because we will just attach a head. The head will have the optical fiber through which the laser is coming. Now you can mount this head in serial, parallel or hybrid kinematics, or in a robotic arm with multiple degrees of freedom. And the way the head will move, your material will be deposited. The bill plate will also have some degrees of freedom. So if the combination of your bill plate and head is having more than 3 or 4 degrees of freedom, then you can print the supportless printing as well. In case of laser, there are few lenses that need to be studied. I think previously also we have studied about the F theta lens, the galvo scanner, the telecentric lenses. So those are the few type of lenses that you use for laser beam. What is more important is in case of wire, you can have the side feeding, you can have the coaxial feeding. For coaxial feeding, it's similar like the electron beam. From three sides, the laser can come, and from the central part, the wire will come. Here, the side feeding is shown. In side feeding, it's not the omnidirectional printing because you'll have the directional solidification in case of this direct side feeding technology. And if you have a rotating feeder, like if we are going from this direction to, if you're going from this direction to this direction, you have one feeding. If you are going in the next, in the opposite direction, you have different type of feeding of the wire. If you're going in the back, you have the front feeding. If you're going in the forward direction, you have the front feeding. So if you have this rotating feeder, you can get the omnidirectionality. Otherwise, if you have this coaxial one, that from the central hole the wire is coming, from the circumferential hole of the nozzle the laser is coming, you can have the omnidirectionality, where it's called the annular beam because this main beam is splitted into multiple beam, and this multiple beam is coming from all the direction from the circumferential slot, and you get this annular type of beam. Another is split beam. So you have only one source, but you have split it into two or three or four or six number of lasers, and then all the lasers are coming in a coaxial mode. So then this is the robotic arm setup with the side fitting. You can see laser laser wire DD. It's very beneficial with comparison with EV based wire AM, because here you can actually operate it in an open atmosphere, not even in a controlled atmosphere. You just need to have a very good shielding with the organ. in open atmosphere, you can print a very large part. So that's why laser wire AM processes are very, very useful these days. They have lot of applications. They have, uh, I mean, lot of real application where people are actually using laser wire AM process to manufacture big parts in rocket engine, in NASA ISRO also you can find. And also, there is another classification of it where we use powder as a raw material instead of wire. But in that case, your powder is very expensive. But wire is also inexpensive thing. So you can print actually a bigger part at a lower cost. These are the this. There was a video which was shown that from the laser pointer that we use for presentation, if you put two slides here, you can split the beam into two and then you can refocus this two splitted beam at one point on the build plate where you can do with the laser. So this is the most important slide according to me, that what are the main process parameters for this laser metal wire aim process or laser wire DD process? So according to me, the foremost or the most important parameter for any laser based aim process is the scan speed, because scan speed tells us what is the interaction time of the laser beam at the time of deposition with your feedstock material, depending upon which you get how much energy is getting transferred. Knowing the power of the laser beam. So power, combination of power and scan speed gives us the main property of the deposition. And then if it's wire based, then wire feed rate is another thing with the uh, speed of the printing as well. So if I divide this process parameter set into four category, then one is thermal energy, feeding, material design, and motion. In for thermal energy, so thermal energy is based on the laser. So laser power is one thing. Then laser spot diameter is one thing. Because if your laser is like this, or your laser is like this, so this spot diameter will actually give me how much power density is coming at the deposition. Even if your laser power is same in both the cases, it's, for example, in both the cases, your laser power is 200 watt, but your spot diameter in one case is 10 mm, and in one cases your spot diameter is just 1 mm. So obviously the power density will be much more in the second case, which is actually reaching the metal, which is helpful to melt the metal. So that's why along with power, beam diameter is important. Then the important thing is beam profile. Profile means whether your laser beam's intensity profile is looking like a Gaussian beam or a top or an annular ring or with a multimode. What is it? Depending upon that, I can tell you that how efficient the power density is, which is actually helping to melt the metal. So beam profile is that much important. Then the working distance. So working distance is again important if I think that like if my focus spot is far away from the build plate or my focus spot is just at the same level of my build plate. So the power density will vary in both the cases. And the wavelength, because wavelength is directly related to the absorption of the laser in the metal. The less the wavelength is, the more the absorption will be. So if I talk about how the laser get absorbed in the metal, then I have to write this well-known equation that E equal to hc by lambda. E, we all know what are the parameters, but this E depends on inversely proportional to the lambda. Lambda is the wavelength. Now, when I lower down the wavelength, my energy is going to increase. So if I'm using a less wavelength laser, my energy of the laser photons are more than when we are using a higher wavelength laser. So if the energy of each photon is more, then we can transmit more energy to the metal, which will in turn melt the metal or help to melt the metal. So that's why E will be more in case of less wavelength. So when we decrease the wavelength of the laser, the absorptivity increases. So आसान भाषा में बोले तो if my absorptivity is more, then less power can melt the metal easily rather than higher power. If you are putting less power, then your cost is also going to be same. So that's why in a running process, you cannot change the wavelength. Changing the wavelength means changing the whole setup of the printing using a very different laser source itself. So it's not a process parameter wavelength, but if you are using a different setup, a different laser source, then you can have different property of the printing, different process parameter as well. Then comes the feeding. So feeding direction, feeding position, angle, these all are coming under the directionality of the printing. Wire feed rate is important along with the gas flow rate. Gas flow rate will give us how to avoid the oxidation without disturbing the melt pool. It should not be like your gas flow rate is so much high that your wire, your melt pool is disturbed. This should not happen. Then your material and design. So the material of the wire, the diameter of the wire, the material of the substrate, these all are the things that is giving me the actual, the property of the after deposition. Then motion may, scan speed is the most important. Track overlap are important to get the stability in the printing and to avoid the porosity. Deposition path, interpass time, preheating temperature. These are important to control the after property of the deposition. Type of or range of process parameter given. This is the type of bead that we get depending upon different type of transfer. So this is the droplet transfer. We can see the droplets. This is a bridge transfer. Because of the bridge transfer, the melted molted droplet is getting the bridged by with the previously deposited layer or the bead. That's why we get a very smooth bead. So this is the bridge transfer. It should not happen that your feed rate, your wire feed rate is so high that your deposition rate is not that high. So why your wire is getting buckled, or your wire is getting, yeah, buckled or broken in the printing, and your deposition is not proper. Then we have a sum that you will get in the question as well. This is the equation where this absorptivity and the power is directly related to the metal thermal history, how it's going to absorb the metal and to melt for the latent heat of transfer from the ambient temperature so that you can get the proper melting of the metal. So thus we can we are ending the wire based processes. Then we are going to the powder aim processes. But before that, I have the Mentimeter today. So I think it's better to go through the Mentimeter first because the Mentimeter is having most of the questions from the week 8 lectures. That is the WAM process. So it will be a recapitulation as well. So I would like to ask all of you to scan this QR from your mobile phone. It's a very simple game. You have already attended, I think. If you haven't, then you have to put your name. It's better to put your real name, and then there will be questions and answers, MCQ, very, very easy MCQ questions. And you have to answer the MCQ question in your phone. There is no real point in this game, but there is some fun point. So you will get point on your right answer, and you will get minus point on your negative on your wrong answer. And if you answer quickly, then you'll get bonus points. So it's kind of a fun activity, nothing else. But you can get a good recap of your last from your last lecture classes.
Ma'am, actually for week 8 solution, I think they have put week 10 solution instead of week 8.
Oh, I think you can mail them for the correction.
Okay.
Yeah, so you can join with you can go to menti.com in the Google and then use this code to join. Or you can directly scan this QR code. I will request all of you to join. I could see only one person joined. Others, Anand and other people can join. It's a fun game. Don't worry. There is no real marks. Okay, I'm starting it.
Ma'am,
So
today's lectures I couldn't join in the beginning, so will I be able to access it?
yeah, you will be able to because it's from the last week's lecture, from the WAM processes.
Okay.
So you can join. No issue. You can go to menti.com and use this code to join. 78140192. So
What is
tell me
this?
when you're yes.
What is the site you told,
What is
madam?
the site?
Site you site.
Menti.com. MENTI.com. It's written here.
Menti.
Menti. Menti.com.
MENTI.
Yes. Or you can scan this QR code also from your Google Lens or normal camera.
Provision is not there. Menti.com. If I type the code, what is the code?
7814 0192. 7814
Yes. 0
0192. 192.
0192.
Yes. Yes, I can see another person. One more is left. Anand, I think. Yes, three people have joined. Three have different
Join.
emojis.
Ma-
Yes,
Just 1
join.
minute.
Yes.
I'm ready. Join quiz. Get ready
I
to
think
play.
you have joined. It's showing here.
My name is Ramana.
I can't see the name right now, but I can see three emojis. So as soon as the question comes, there will be options.
It's not a
You have to mark the right option according to you, but you have to be fast because the fastest one will get more point. So you have to be fast in answering the question. Don't worry, there is no real marks. It's just a fair fun game. So I could see two players. One is coming and going and coming. So now I'm pressing enter. So the question will start coming. So here is your first question. In VAM, one of the main metallurgical challenges during deposition. Two people have answered and they have answered correctly. So it's because as it's a repetitive thermal heating and cooling cycles going on, so high residual stress will be there. And this process is this problem is not only present in VAM, but it's present in any kind of metal aim processes which involve this laser, arc, or electron beam. So now we can see the result. एक ने लेफ्ट कर दिया क्या quiz? Let's see if he can join again. I think his network is not stable because he is coming and going. Okay, so now I am going to my next question. One player is ready, I can see. So here is your second question. You can join anytime in between.
The main thermal degradation of polymer.
So the thermal degradation of polymer in the liquefier is more likely when residence time of polymer melt in the hot zone is long, build plate temperature is too high. So the degradation in the liquefier is not related to the build plate because both the things are going on simultaneously but not interrelated. But the polymer melt in the hot zone, if it's too long, then thermal degradation will happen because you are over melting the polymer in the liquefier. So there is no point.
Right answer is
The too prolonged melting of the wire in the liquefier. The third option. Here comes your third question.
polymer melting. So the following is a key advantage of RAM or powder based direct. This is the
The advantage of YM over powder based is higher deposition rate and material utilization efficiency. Because if you are going to now we are going to discuss about powder, there you will see there is lot of wastage in the powder based aim which is not present in the wire, and the deposition rate is higher because the wire is a very thicker thing than the loose powders. So that's why deposition rate is also more in wire as the wastage is less. So better control of part porosity due to low cooling rate. Low cooling rate I would not recommend, but part porosity is obviously greater, but I can't say low cooling rate. So that's why this second option is controversial. The right answer is higher deposition. Okay, no point. No worries. Here comes our fourth question.
PAM source system. First one is the answer. VAM means welding
Yes,
only.
yes.
Whether it may be TIG or MIG.
Yes. Okay, we have the same fastest Anand. Next, it's our fifth question.
That most significant. Great job. Three. Incorrect.
Which factor most significantly influences bead geometry, wire feed rate, and travel speed? Filament diameter uniformity is like when you're using the wire, now it's the standard wire. So filament diameter will not be that helpful in this answer because filament diameter will be uniform only. And then platform adhesion techniques is like if your adhesion is not good, then your overall printing is going to be destroyed. It's not related to one bead geometry or something. Your printing will not be good. Even you will not even get the printing after the whole process. But wire feed rate and travel speed, if the combination is not good, then some portion you'll get a mota bead and in some portion you'll get the thinner bead. So that's the answer. No points. Then comes our sixth question.
Better control. Mechanical anisotropy. FDM. Primarily due to mechanical strength.
So weak interlayer bonding between the successive extrusions uh, is mainly due to the mechanical anisotropy. Residual stress is not that much. FDM means it's a tricky question basically. FDM means the material extrusion where you put the coils for the heating in the nozzle and the wire get melted in polymer. Remember? So FDM is not the wire process that you'll get the residual stress. So
The
no
FDM
point.
is limited to polymer only.
No, FDM is not limited to polymer. You can have the metal FDM as well. But in case of metal also, the residual stress is not that much prominent because there is no direct interaction of the heat laser beam or such high energy beam with the metal. It's just the resistance heating. And arc plasma anyway is not present in FDM. It's the material extrusion process. It's not directed energy deposition. So
So
let's
residual stresses
see.
will be less.
Yeah, residual stresses will be less and it will not be a very something to be concerned of. It will not be very high because your heat source is not that much high itself. It's not a high energy laser or electron beam. Okay. So I'm going to the next question.
Getting.
Okay, well plate temperature. Good. Then we have next question.
Parameter.
Eighth question.
Semi-crystalline.
FTM has a major limitation with respect to WAM.
And
Yes. Next. I think there is somebody trying to join, so there was a sound. Yes, so here is our ninth question.
also.
Ah, what happened? Okay, so yes, it was right. So we can go to the next question. Something happened in between, so there was an error. Okay, let's go to the 10th question. Main mode of metal transfer in MIG. Again, somebody is trying to join. So the main transfer mode is spray transfer in MIG. In MIG, cold metal transfer is in CMP. That is the cold metal transfer mode. But MIG is the consumable wire. So it's the spray transfer. Next question, 11th. Start.
Madam, please allow me to join with another device.
Okay. But I don't know
I have some
where it's not
battery
opening.
problem. I have some battery problem. So I wanted to shift to
Yeah.
some other device.
Okay, just a second. I'm trying to go to the, yes. You have joined, I think. Yes.
Yes. Thank you.
Yes. So it was right answer. Let's go to the next question. Here is our 12th question. Large heat affected zone and distortion. Right answer. Next is our 13th question. The deposition efficiency is around 40 to 50%. It's wire based, that's why this much. When it's about powder based, even it's 20 to 30%. Is our next question. 14th. I think only one person is attending. Or both the person people are attending. I don't know.
Only one.
Only one. High feed rate and welding correct. Next is the second last. So the arc stability is because of the voltage and shielding gas composition. So shielding gas composition is also important, or shielding gas parameters are important for the arc stability as well as weld pool stability. And voltage is obviously the one thing because it's arc arc is getting produced because of the whole voltage source. So that's the answer. Next is our last question. Yes, they balance arc stability, penetration, and cost. So we have only one participant, so one winner. But anyway, next class we will do the 20 on powder based aim. So let's continue our discussion on the powder aim. So by this time we know about the wire based aim. The main advantage of powder aim is that you can print a very precisely featured parts. So your part feature is more, can be more. Another thing is, as you're using powder, so there is a lot of flexibility in mixing different type of powders. So making metal matrix composites, high entropy alloys, functionally graded materials are very much flexible in powder-based aim rather than wire-based aim. But there are a lot of disadvantages as well. In powder, there are more chances of porosity because loose powders are depositing. The second most is the wastage. A lot of powder gets wasted. So the efficiency lies in between 20 to 30%. And also the powder is very expensive, very due to high wastage, it's more expensive. And when you're depositing the powder, there are some best powder particles. You can collect them and reuse them after sieving. But if your powder is very much high prone to get oxidized, like aluminium or titanium, your powder will be oxidized. And even after sieving, the powder will not be very helpful in your further printing. So these are the main pros and cons. Now going through the process. So in powder based aim also you can have laser based powder based DD process, or electron beam or plasma based processes. But electron beam based DD of powder is not possible because you are printing in vacuum. And in vacuum, you cannot do the powder feeding because powders are loose particles. It's not like wire that it will come through the nozzle simultaneously with the electron beam and rigidly. It's not possible with the powder. So powder fed electron beam aim is not possible. But under the powder aim, we have laser powder bed fusion as well, and electron beam powder bed fusion as well. So we have the ninth classification of aim, which is powder bed fusion. In that, you have laser PBF and electron beam PBF. And in case of powder DD process, directed energy deposition classification, you have powder fed laser DD process and plasma powder fed DD process. So one by one. So first is the working principle of powder feed, etc. So it's basically you will have a nozzle. This is the laser nozzle. This is the powder nozzle. So from powder, the powder is fed, and through this the laser is coming. It can also happen that in your nozzle itself, you have few slots for powder. These are the slots inside, and through these slots, the powder is coming. and coaxially from the central slot the laser is coming. So that is the main difference between wire and powder DD process. In wire DD, the wire will come through the central slot and the laser will come through the circumferential slot, whereas in powder the laser will come through the central slot and the powders will come through the circumferential slot. This configuration is basically to increase the capture efficiency. Capture efficiency means how much raw material you are feeding and how much is getting deposited. The ratio of it is the capture efficiency. In case of powder, the capture efficiency is very low, but in case of wire, it's better. And now, just a second. Then this is the typical schematic of the DD machine. We can see the powder delivery system. So powder delivery system is basically the powder hopper. It will be a separate small machine through which the powder will be coming using through a pipe. Now, as we are using a separate tool for the powder delivery, you can put two different powder here, and these two powder can be mixed and simultaneously coming through the deposition. And they will come through argon gas because loose powder cannot come through vacuum or something. So I need an inert gas to flow the powder from one container to my deposition zone. So that's why this powder chamber will be connected to the argon, and now the powder is coming to the deposition zone. This is a mixing chamber. So this mixing chamber is important when you are mixing two different type of powders together to get an MMC like metal matrix composite or functionally graded material or high entropy alloy or any special type of alloy that you want to print.
Does this two chambers contain different type of powders?
Yeah, it can. So it can be like there are two different powders for, or there can be only one hopper with one powder. If you want to mix two powders and then print, then you use two hoppers with two different powders. Otherwise, it's also okay to print to pour the powder in one disc and from one disc directly come to the deposition chamber. But whatever the powder comes, it will come through the argon gas itself. Otherwise, the powder अकेला तो नहीं आ सकता ना. They are loose powders. So the argon gas carries the powder. So the argon gas here is called the carrier powder.
So argon gas will help in carrying the powder from the powder chamber to the mixing chamber.
Yes, yes.
Okay.
And this now as argon gas is carrying, so and also we use a separate argon gas for shielding to minimize the oxidation, to protect the melt pool from the oxidation and foreign particle entrapment. So these carrier argon gas will also have some separate parameter such as the feed rate of the or the flow rate of the carrier gas. Depending on the flow rate, you will have the feed rate of the powder. The powder feeding machine can be of various designs depending upon which you can fix the parameter, but this argon flow rate will be constant. So next, DD cannot print any polymer. It can only print metal. And now comes the various ways how you can deliver the powder. So these are the conveying system. So this is kind of a conveyor. So through this, when it rotates, it carries the powder and come to the stirrer. The stirrer will stir the powder together if we are interested in mixing two powders. And then through this nozzle, the argon gas will carry the powder to the deposition zone. Next, it can be piezoelectric ring. So this is a material called piezoelectric material. Piezoelectric material is nothing but when a material vibrates upon giving some voltage. So it's kind of the electrical to mechanical energy converter. There are type of material where if you put voltage or if you supply voltage into it, they get contract or they get expanded. So basically they will expand or vibrate. So when they do that, this powder will start coming out of this zone. So the powder will start coming here and then eventually they will come to the nozzle and through which it will come to the deposition zone. And if you are interested in two powder mixing, then two type of this thing will be there. This is the piezoelectric material. This is the piezoelectric material which vibrates through which the powder is coming. It's getting mixed in the stirrer or mixer and then comes to the deposition zone. Then there can be this, as I said, there can be the coaxial nozzle also, where your central hole will be present for the laser, but through circumferential hole, the powder will come. In that case, after the mixer, the powder delivering nozzle pipes will be splitted into two, and then as a इसके circumference say the powder will start coming to the deposition zone. So through several tubes you can feed the powder from all over the area in the circumferential slots, and you can get an annular ring in the, so basically if you see the top part, through this portion the powder will come and through this the laser will come. This is laser and this khali jaga is for powder. This dot are the holes uniformly spread in the circumference of the nozzle, and through these dots the powder will come. So the powder will make an annular ring at the deposition zone. So as it suggests, there are various type of powder delivering or powder conveying system present in the market. Different machine rotates in a different way to give the powder. Here there is a hopper where you pour the powder. This disc rotates, and when it rotates till here, because of the vacuum pressure, it sucks the powder out, and through which there will be inert gas, and through the inert gas the powder flows here, the carrier gas, the powder flows to the deposition zone. The different type of powder conveying system will be there. Now, as I'm talking about powders, these powders will have a size distribution as well. It's not like a very fine powder. It's not like a very coarse powder, but they have a very specific size distribution. So the powders will have 45 to 120, 40, sorry, not degree, what I'm writing, 45 to 120 micron. Forty-five to 120 micron is the typical powder distribution or powder particle size distribution that we use for DD. So you need to understand, when I'm saying this is the typical range of the powder size, that means this powder can can be delivered through these systems. Whatever has been discussed, this conveying system, this rotor pneumatic method, this vacuum method, steering, gravity-based method, whatever method is there, these methods are capable of feeding powder with this much size only. When the size decreases, if your powder is having size distribution 1 to 10 micrometer or 100 nanometer to 1000 nanometer, then your these systems will not be able to feed the powder. You have to change the feeding systems, because you can imagine if the powder size is very less, their flowability will decrease and they will not have the same flowability. That means they may get clogged inside the pipe and you'll not get an uniform flow of this powders. So that's why then you need to change the powder feeding technology, and there are few ultrasonic vibration techniques through which you can deliver the powder. So that will be discussed in the next class. Till this class, there are this powder feeding technology. So one can be this side feeding, then it can be coaxial feeding with the circumferential slot. So it's kind of annular ring. But here it's through 4 slot the powder is coming. Here the powder is coming through central slot and the beam is splitted into the annular ring. Here the beam is splitted into 3 and the powder is coming through center. So these are few combinations that you can use for this DD technique. DD came from the cladding, that is the repairing of parts. So repairing of part using this powder feed DD is very easy and better process than other. And this is the typical schematic of DD. From the next class, we will be moving on to the in detailed discussion on powder DD.
And so on powder fed DED, instead of the metallic wire, we will be giving powder, right?
Yes, metal powders. So now I think we can move on to the previous year questions. You know the answer. What is the impact of decreasing the work function of the metal on thermionic emission? So it increases the rate of thermionic emission by lowering the energy barrier for electron escape. It's from the electron beam side. In the context of electron based electron beam based wire AM, select the correct option. Option 1 is electrostatic field is used for the extraction and the acceleration of the electron beam. Magnetic field is used for focusing, deflecting and correction of the beam.
Only one is true.
1, 2 is also true because magnetic field, magnetic lenses are used for focusing. Na? You were not there, I think, at the beginning of the class.
Yes.
So both are true. So the work function of a material in the context of thermionic emission is the minimum energy needed to release an electron from the surface of the material. In the context of EVA wire AM, first option is electron beam is focused by electromagnetic coils. Second is to correct the shape of the electron beam, stigmator coil is used. So it's both are true. Electron beam focused by electromagnetic coils, as we have seen in the second question. To correct the electron beam shape, we use the stigmators. In thermionic gun, the range of acceleration voltage is dash in comparison to plasma gun. So it's more, and while life of plasma gun is more in comparison to the thermionic gun. What is the condition for metal transfer in wire-based electron beam additive manufacturing, where h is the distance? So the r is the critical radius of the droplet should be lesser than equal to 0.5 of the distance between the tip of the wire and the substrate. To melt a 1.2 mm diameter stainless steel wire, what should be the acceleration voltage in volts? So we have a formula. So P equal to power equal to V into I. Power required to melt is will add the melting of the wire and the latent heat of fusion, latent heat transfer, and equating 1 and 2, we get the voltage. So here you can place V into I, and then all the things are current 1 ampere current I mil gaya. V we need to find out d square. D is the wire diameter 1.2. Bf is the feed rate. Then rho is the density of the wire. Then Cp is given. Tm is the melting temperature. T naught is the room temperature, 25 degree. Latent heat of fusion is 260 kg Kelvin per kilogram. And when you put all the values, you get the voltage. That is 331.6. You can note down this formula and later on you can use it for other sums or for the practice.
And for current, what will we put in equation 1?
Electron gun current 1 ampere written here.
Okay.
Next, you can write down the formula first. So for a very low feed rate of wire in laser metal wire aim, which type of wire deposition characteristics will be observed? So it's the wire dripping method. 8 is the sum that we were discussing. It's the same sum. So the process map corresponding to inconel 625 wire having a radius of 0.7 m means the diameter is 1.4 mm is shown in figure. So the energy per unit length of track is given here and wire deposition volume per unit length of track is given here. For laser power of 1.7 kilowatt, traverse speed of 1.7 mm per second, wire feed rate of 8 mm per second is given. So wire deposition characteristics. So EL is the energy per length. So it's given P by VT, which is given as the laser power 1.7 into 10 to the power 3 watt by the traverse speed of 1.7 mm per second. So now we get the joule per mm energy, which is equal to 10 to the power 3. Now the VL, that is the wire feed rate with the respect to the length, is given by this formula, this R square into 8 mm wire feed rate by 1.7, this traverse speed, which is given 7.24. So that means as it's coming 7.24, that is in the third zone. If you see from graph, 7.24 means it's coming near 6 to 8. Here 7.4. which is coming as the, what should I say? In the third zone, it's the smooth wire transfer. It's written here, if you see that traverse speed, red one are 1.7, it's 3.3 when the zone is here, and it's 5 mm per second when the zone is here. Our traverse speed is already here, and now our velocity is coming near 7.24. So that means my zone is 3, which is the smooth wire transfer. For the detail of this sum, you can go to the second PDF of week 9 lectures, and you will get a detailed demonstration of how all other parameters also you can find out from this type of graphs.
Is it based on VL is greater than EL? Or
Sorry, can you repeat?
how do we selected this choice that is smooth wire transfer?
So that's what I'm saying. To select the choice, first you have to see the wire deposition per volume length is VL, where it is coming at 6 to 8. And now we have the EL, that is 10 to the power 3. So it's coming in this third area anyway, because my traverse speed is also 1.7. So it's the third area only. And then my volume, this wire deposition volume per length is coming in here. So that means I'm coming in this third zone. Third zone means the smooth wire transfer. Which zone indicate which type of transfer depends upon what is the VL value coming with respect to what is the traverse speed. And the detail of this thing is given in the second PDF. So you can find where we have to select the stubbing, where the dripping will come, or where the other mode of transfer you can select. Here, as it's coming in the middle zone, it's the smooth wire transfer. Okay. Other zone is also written here, that what is the relation between this VL and the traverse speed, which combination you get where. So then we have the ninth. In the above question, for the same wire radius of 0.7 mm, the wire deposition characteristics will be EL is already given 800 joule per millimeter. VL we can calculate from the formula. From the figure, it should be smooth wire transfer, like the previous formula. It's the same. Even if the wire, this already it was given the traverse speed is 1.7. So I know my zone was here and not down here. But now the traverse speed is not given, but it says that your energy is 800. That means the zone is kind of here only. And same, the VL is coming around this 3. So that means the smooth wire transfer. Then the type of wire deposition characteristics is observed when the available energy is low and the wire entered the melt pool is nearby solid form. So it's the wire stubbing. That means your wire is not getting melted because of less energy density, and your wire is not getting melted, it's just getting fused, or even you can see solid form of wire. The type of wire deposition characteristics is observed when the available energy is sufficient enough to melt the wire tip. It's a smooth wire transfer. That is what we are trying to achieve in any case of wire metal transfer process. What will be the surface tension of what will be the surface tension force of the stainless steel wire of 2 diameter having the feed direction of uh, 30 degree. It's 30 degree, not 300. I don't know. It's 30 degrees. The formula is not given here. You can find the formula in the PPT. It's very easy. Which type of vacuum pump is used for low vacuum? It's the root pump. That is the lowest one. And if you have another option, rotary pump, then rotary pump can give you even lower vacuum. So as now we have root, turbomolecular and diffusion, we will choose root pump. If the options are like root pump, turbomolecular diffusion and rotary pump, then your correct option will be rotary pump. Now this type of nozzle is shown. So it's discrete nozzle because through 4 discrete pipe the powder is coming. It's not the annular kind of ring. So it's not continuously powder is coming like annular shape. It's the discrete coaxial nozzle. But through central slot the laser is coming. The red one is the laser. Type of nozzle create an asymmetric powder temperature laser intensity resulting melt pool. It's the lateral feed or off axis nozzle because it will not give me omnidirectionality. So there will be asymmetric powder temperature or powder deposition characteristics or directional solidification. For a given setup and the indicated moving direction, the orientation of wire feed is basically the back feeding. It's back, the laser is at front, so the wire is coming at the back. So back feeding. The laser beam split it into two halves. Which of the following? It's the prism. Next, the lateral feed powder delivery nozzle can be
Ma'am,
used.
previous screen, can you show once more?
Sorry, can you repeat?
The laser
I
beam is
can't.
split into two halves by. Okay.
Using the which system. So it's the
Okay.
prism system through which
Okay.
there will be only one laser beam coming and then they get splitted into two, and this two laser beam will have different plano-convex lens to focus at one position. So they get splitted into two beams using the prism system, prism type of lens or prism type of mirror.
Now for question number 17, how can we tell this back feeding?
So here, if you see the diagram carefully, it's the laser is the red one, which is coming at the front, and the wire is coming at the back. And from the back, I can see some melt pool is here. If you see carefully, the melt pool is behind the laser beam. In actual, you can see clearly that the wire is coming from the back, but at the picture, it's difficult to understand. So what is done here is this is the melt pool. Okay, if you see, this is the bead. This bead is solidified. This ash one. This is reddish one. That means it's just got solidified. And this red hemispherical thing is the melt pool, in which this red is the laser beam, and laser beam is at the front of the melt pool. The melt pool is getting formed using the wire. And if the melt pool is behind the laser beam, that means the wire is coming at the back. If it's front feeding, then you could see the melt pool and the wire at the front. And if it's side feeding, then wire will be a little bit down, and at the side till this point of the side, the wire would come. But here the wire is coming at the back and your melt pool is at the back of the laser. That means it's back feeding. It's just a tricky question because it's an image. If it's a video, it's easier to say.
By feeding, they mean how the wire is fed.
Yes, yes. Feeding means the feeding system.
Okay.
You're feeding the wire here. So wire feeding. Okay. So next is lateral feed powder delivery nozzle can be used to deposit uniform tracks while cladding of cylindrical workpiece, primarily because it can maintain consistent feed orientation. Select the incorrect statement. Inert gas is used as a plasma medium. In the context of powder delivery nozzle in the context of powder delivery nozzle. So inert gas is used as a shielding of the melt pool. Inert gas is used for delivering the powder. Inert gas is used for laser optic protection. But used for shield plasma medium is not true for the powder delivery nozzle in powder fed additive manufacturing, right? So that's why in this context, this option is wrong. That plasma medium and inert gas concept. Okay. These are few 2 years back questions. I would like to discuss few of them. So in which type of electron emission heat energy is provided to emit the electrons? So it's the thermionic emission. Velocity of the electron is increased by the acceleration voltage because we are giving the voltage source to get the electrons out of it. Which type of vacuum pump is used for low vacuum? It's again the root pump, but if you have the rotary pump option, then rotary pump gives us the lowest vacuum. Electron beam is focused by electromagnetic coils. And laser beam is focused by optical lenses. To correct the shape of the electron beam, which type of the coil is used? It's the stigmator. So stigmator coils are used to correct the shapes. To focus it, we use the magnetic lenses. And for the delivery, we use the electrical, it's the same electromagnetic lenses. What is the condition for metal transfer in wire-based EB?
Our last option.
Yes, it's the same. Then we have matched the following. So try to do it, it's easy.
A2B1C.
Okay, so electron beam is electromagnetic lenses, laser beam is galvometer, and plasma beam is shielding gases. So A2, B1, and C3. Why vacuum is required for electron beam? So it's because lot of things. Focusing of electron beam first, because electron beam is made of electrons and electrons are very lightweighted. So if we are purging the electron beam in a normal atmosphere or air filled chamber, then the air molecule or air particles will try to interact with these electron beams. And air is having what? Nitrogen, oxygen, carbon dioxide. These are much more heavier than electron. Electron is the lightest thing. So the electron will get deviated from its path and they will not be able to focus at a particular position. So that's why we need the vacuum. The cathode life will also be reduced if we are doing it in air because of the air molecular interaction with the cathode and good material integrity of the part. These are some indirect ways, but all of them are true because if we are doing it in vacuum, you can maintain the purity of your metal. You can avoid the oxidation. You can avoid.
For question number 9, actually, all these actually electron beam and electromagnetic lines, how are they connected? That I don't know.
Okay, so the electron beam are a beam made of electrons. In case of laser aim process, if you remember, we were focusing the laser using the plano-convex lens. It's basically the convex lenses, F theta lens or telecentric lens, whatever you need. But you have a physical glass lens to focus a light, and laser is a light beam. But electron beam is not a light beam. Electron beam is made of electrons. So if you put a lens in front of electron beam, the lens may absorb the electron, or it will not be transparent to the electron, or something else can happen. For electron beam, we need a different lens to focus them. So in that case, we use electromagnetic lenses. Basically, we put two electromagnetic coil at the two sides and through the middle part. So imagine you have electromagnetic coil here and here, and from middle the electron beam is coming. So these electromagnetic coils have a rotary. Obviously, these are the electrical. What should I say? The electricity is going on to it. So moving electricity is giving us the magnetic effect. And because of this magnetic effect, the electrons will get repelled from these two electromagnetic lenses, and they will be coming to each other. So as a result of which they will be focused at one point. So it's not a physical lens of glass, but it's the electromagnetic coils that we put at two sides of the electron beam to make it focused. So that's why electron beam, we use electromagnetic lenses. But in case of laser beam, we use the physical plano-convex lens or galvometer or F theta lens. Now is it clear? I think it's okay. And as I was discussing about this 10th point, so if
So
you are
plasma
printing,
beam, plas
yes,
plasma beam and shielding gas are connected by how are they connected?
because see, if you have these three options, then only the plasma beam and shielding gas are there present. So that's why they are together. So you can see in case of plasma beam, we get the plasma beam by electrically charging the gas. And like that, you can match plasma beam with shielding gas. Electrostatically, we charge the gas particle, and because of the discharging of gas particle, we get the ions out of it, which is basically the plasma beam. And this plasma beam is gas discharge, so we put the shielding gas to make it in a concise, focused way, so that my melt pool will have a shape and my deposition will have a shape. So like that, the plasma
But
beam is related to the shielding gas. Anyway,
but
laser
usually
beam,
shielding gas is it used for protection from oxidation?
yes, yes,
Okay. But in this case, it is not like that, right?
yeah. Then next question is the metering unit in powder feed base aim primarily accomplishes the task of control of powder mass flow rate. To avoid the anisotropy in part fabricated by powder feed aim, which of the following nozzle should not be used? This is the lateral feed. To avoid anisotropy, lateral feed is not good. Only if you are interested in the directional cladding, then the lateral feeding is okay. Otherwise, if you are using lateral feeding, you will have this directionality, so your part will be anisotropic, and isotropic cannot be achieved. So Coaxial one is better for isotropy. Axicons in laser optics head are typically used to achieve which of the following laser beam? It's the annular. It's kind of a setup name. The laser metal wire additive manufacturing, the phenomenon of wire dripping primarily caused due to very low wire speed. That means the wire feed rate is very, very low. It's the same option. The select the incorrect statement made in the context of powder delivery nozzle in powder feed based additive manufacturing. So select the incorrect. So the plasma medium, the same one. And here also is the same question. In case of this thing, it's the back feeding. It's not the front feeding. As you can see, it's the wrong option. Here also in this photo, at the back, it's coming. So it's the back feeding. Okay. Not front feeding, it's back feeding. Like that. I was having only these questions with me. If you have any doubt, you can ask me. Otherwise, I can stop my class.
I will
And
go through the lecture, and if there is any doubt, I will mail you.
yeah, sure. You can mail me anytime. Otherwise, anyway, in the next class, I'll try to make the mentee on these topics, what we have covered today. Then we will have a recapitulation in the next class. Okay, then I would like to end the class here. Thank you for attending.
Thank you.